Picture a tiny speck of rock, adrift in the vastness of space, smaller than a city, yet holding secrets that could rewrite the story of our solar system. For billions of years, these unassuming asteroids have danced in the gravitational embrace of Jupiter, silent witnesses to the cosmic chaos that birthed the planets. They are the Trojan asteroids, ancient relics of a time when the solar system was a crucible of creation. But in 2023, a spacecraft named after a fossil that reshaped our understanding of humanity's origins uncovered something extraordinary, an anomaly so improbable it defies everything we thought we knew about these distant worlds. NASA's Lucy mission, on its audacious journey to explore these time capsules, stumbled upon a discovery that shouldn't exist: a pair of asteroids, locked in a delicate cosmic waltz, revealing a structure so bizarre it challenges the very laws of physics and geology. Join me today as we unravel this astonishing find, explore what it tells us about the universe's past, and ponder what it means for the future of our cosmic understanding. 4 billion years ago, the solar system was a turbulent nursery of gas, dust, and rock. Planetesimals swirled in chaotic orbits, colliding and coalescing to form the planets we know today. Amid this frenzy, some fragments were caught in a gravitational net, trapped at stable points in Jupiter's orbit known as Lagrange points. These Trojan asteroids, numbering in the tens of thousands, have lingered there ever since, preserved like fossils in amber. They are not mere space debris, but pristine samples of the raw materials that built the gas giants. Scientists long believed these asteroids would be uniform, sharing similar compositions reflective of their shared origins. But the universe, as it so often does, had other plans. When Lucy set out in 2021, on its 12-year odyssey to visit these enigmatic rocks, it carried the hope of unlocking their secrets. What it found instead was a phenomenon so unexpected it sent ripples of astonishment through the scientific community. In November 2023, Lucy approached its first target, a small main-belt asteroid, chosen not for its scientific allure, but as a test run for the spacecraft systems. This asteroid, barely half a mile across, was meant to be a simple checkpoint, a chance to calibrate instruments before the mission's true purpose: exploring the Trojans. As Lucy sped past at 10,000 miles per hour, its high-resolution cameras captured something startling. This unassuming rock wasn't alone, it had a companion, a tiny satellite orbiting it. But the true shock came when closer images revealed the satellite's nature. It wasn't a single body, but a contact binary. Two smaller asteroids fused together like a cosmic dumbbell, touching at a single point. This peanut-shaped marvel, the first of its kind ever seen orbiting another asteroid, was a revelation that defied expectations. How could such a fragile, improbable structure exist in the harsh environment of space? To understand why this discovery is so extraordinary, we must first consider the brutal realities of asteroid formation. Asteroids are born from collisions, violent events that shatter and reshape rock over eons. A contact binary forms when two bodies, caught in a delicate gravitational dance, collide so gently that they stick together without merging completely. This requires an almost impossible balance of speed, angle, and material strength. In the main asteroid belt, where collisions are frequent and chaotic, such a structure should be obliterated by impacts or torn apart by gravitational forces. Yet there it was, orbiting its parent asteroid, a testament to the universe's capacity for surprise. This tiny satellite, now named in honor of peace in an ancient language, is a cosmic anomaly, a structure that, by all accounts, shouldn't survive, let alone orbit another body. The implications of this find are staggering. For decades, scientists have studied contact binaries in isolation, noting their rarity across the solar system. They are thought to form in environments where collisions are slow and gentle, perhaps in the distant Kuiper belt where objects are more loosely bound. But finding one orbiting a main belt asteroid suggests that such delicate formations might be more common than we imagined. This challenges our models of asteroid dynamics and raises profound questions about the conditions in the early solar system. Were these asteroids once part of a larger body that fragmented, leaving behind this fragile pair? Or did they form independently only to be captured in this improbable configuration? The answers lie in the data Lucy collected, which scientists are still painstakingly analyzing, piecing together the story of this unlikely duo. Lucy's encounter with this asteroid was no mere accident. The spacecraft, equipped with a suite of advanced instruments, was designed to probe the mysteries of the solar system's origins. Its high-resolution imager captured detailed views of the asteroid's surface, revealing a trough where a massive chunk of rock had shifted, hinting at internal stresses that reshaped the asteroid over millions of years. The infrared spectrometer detected subtle variations in composition, suggesting the presence of silicates and possibly organic compounds, clues to the building blocks of planets. The thermal emission spectrometer measured the asteroid's surface temperature, providing insights into its physical properties. Together, these instruments painted a picture of a complex dynamic system, far more intricate than anyone had anticipated for a test-run flyby. But this discovery is just the beginning. The asteroid and its satellite are not isolated curiosities. They are part of a larger tapestry of cosmic evolution. The main asteroid belt, where this encounter took place, is a region of remnants from the solar system's formative years. Unlike the Trojans, which are thought to originate in the outer solar system, main belt asteroids are closer to the Sun, subjected to intense radiation and frequent collisions. The presence of a contact binary here suggests that the processes governing asteroid formation and survival are more varied than we thought. Could similar structures exist among the Trojans, waiting to be uncovered? If so, they could provide a bridge between the inner and outer solar system, linking the rocky worlds like Earth to the icy realms beyond Neptune. As Lucy continued its journey, it offered another glimpse into the unexpected. In April 2025, it flew by a second main belt asteroid, a fragment of a collision that occurred 150 million years ago. This asteroid, larger than its predecessor, revealed a strikingly complex geology, with craters and ridges that spoke of a violent past. Its elongated shape, stretching 5 miles long and 2 miles wide, hinted at a history of slow rotation and thermal stresses that reshaped its surface. Like the first asteroid, this one was more than a simple rock. It was a window into the processes that sculpted the solar system. The data from this flyby, still being analyzed, promises to deepen our understanding of how asteroids evolve and survive in the chaotic environment of the main belt. These main belt discoveries, while remarkable, are merely stepping stones to Lucy's ultimate goal, the Trojan asteroids. These ancient rocks, trapped in Jupiter's Lagrange points, are believed to be pristine samples of the material that formed the outer planets. Unlike the main belt asteroids, which have been battered by eons of collisions, The Trojans are thought to be largely untouched, their surfaces preserving the chemical signatures of the solar system's infancy. Scientists hypothesize that they may contain water ice, organic molecules, and silicates, ingredients that could have seeded Earth with the building blocks of life. But the diversity among the Trojans, revealed by telescopic observations, suggests a more complex origin. Some are redder, hinting at organic-rich surfaces, while others are greyer, resembling the rocky asteroids of the inner solar system. This diversity challenges the idea that the Trojans formed in a single region, suggesting instead that they are a cosmic collage gathered from across the early solar system. The discovery of the contact binary satellite adds a new layer to this mystery. If such structures can exist in the main belt, could they also be present among the Trojans? The possibility is tantalizing. A contact binary in the Trojan swarms could indicate that the processes of gentle collision and capture were active even in the outer solar system, where conditions were thought to be less conducive to such formations. It would suggest that the Trojans are not just relics, but active participants in the solar system's ongoing evolution, their surfaces and structures shaped by subtle forces over billions of years. Lucy's mission, with its planned flybys of 8 Trojan asteroids between 2027 and 2033, is poised to answer these questions, offering unprecedented views of these distant worlds. The spacecraft's journey is a marvel of engineering and celestial mechanics. Launched on October the 16th, 2021 aboard an Atlas V rocket, Lucy follows a complex trajectory that loops around the Sun 3.5 times, using Earth's gravity to slingshot itself toward Jupiter's orbit. Its path takes it through the main asteroid belt, where it has already encountered 2 asteroids, before reaching the L4 Trojan swarm in 2027. There, it will visit 4 asteroids, each chosen for its unique characteristics, from the collision-scarred Eurybates to the reddish Orus, which may harbor organic compounds. After a third Earth gravity assist in 2030, Lucy will head to the L5 swarm, where it will encounter the binary pair Patroclus and Mennoetius in 2033. Each flyby is a fleeting moment, lasting mere hours as Lucy speeds past at thousands of miles per hour. Yet the data it collects will be studied for decades. The challenges of this mission are as daunting as its ambitions. Shortly after launch, one of Lucy's massive solar arrays failed to fully deploy, threatening the spacecraft's ability to power its instruments in the dim outer solar system. Engineers worked tirelessly to address the issue, using the array's motor to nudge it closer to full deployment. Now estimated to be between 353 and 357 degrees open, the array is stable enough to support the mission, a testament to human ingenuity in the face of cosmic adversity. This resilience mirrors the asteroids themselves, which have endured billions of years of isolation and bombardment, yet continue to hold their secrets. The contact binary discovery is a reminder that the universe is full of surprises, waiting to be uncovered by those bold enough to seek them. It challenges our assumptions about what is possible, forcing us to rethink the physics of small bodies in space. The delicate balance that allows 2 asteroids to touch without merging or separating speaks to the intricate interplay of gravity, rotation, and material strength. It suggests that the solar system is not a static relic, but a dynamic system, where even the smallest objects can reveal profound truths. This find also underscores the importance of exploration. Without Lucy's close-up view, we might never have known such a structure existed, orbiting silently in the vastness of space. As Lucy continues its journey, it carries with it the hopes of scientists and dreamers alike. The Trojan asteroids, with their potential to reveal the solar system's origins, are more than scientific targets. They are a bridge to our past. They may hold clues to how Earth acquired the water and organic molecules that made life possible. The discovery of a contact binary in the main belt hints at the complexity we may find among the Trojans, where similar structures could reveal new insights into the processes that shaped the early solar system. Each flyby will add a new chapter to this story, building a mosaic of data that could transform our understanding of our cosmic neighborhood. The philosophical implications of this discovery are profound. The existence of a contact binary so fragile yet enduring invites us to reflect on the resilience and fragility of the universe itself. It reminds us that even in the vast, indifferent expanse of space, there are moments of delicate beauty where the improbable becomes reality. This tiny satellite, orbiting its parent asteroid, is a microcosm of the solar system's history, a story of chaos, collision, and creation. It challenges us to question our assumptions, to embrace the unknown, and to seek out the unexpected. In a universe governed by relentless physical laws, the improbable can still happen, and it is through exploration that we uncover these hidden wonders. The road ahead for Lucy is long and uncertain. By the time it reaches the Trojans in 2027, it will have traveled billions of miles, navigating the complexities of celestial mechanics with precision and grace. The data it collects will not only answer questions about the Trojans, but also raise new ones, sparking debates and discoveries for generations to come. The contact binary discovery is a preview of what's to come, a glimpse of a universe that is stranger and more wondrous than we ever imagined. As we await Lucy's arrival at the Trojans, we are reminded of the power of curiosity, the drive to explore, and the courage to confront the unknown. In the end, this improbable discovery is more than a scientific milestone. It is a testament to the human spirit. It shows us that even in the vastness of space, where distances are measured in light years and time in eons, there is room for the unexpected. The contact binary, orbiting its asteroid, is a symbol of the universe's capacity to surprise, to challenge, and to inspire. As Lucy journeys onward, it carries our questions, our hopes, and our dreams, seeking answers in the ancient rocks that have watched the solar system grow from chaos to order. And in their silent orbits, these asteroids remind us that the universe is not just a place of laws and forces, but a canvas of possibilities, where the improbable can become the eternal.